In today's video, I'm going to look at the second half of section 6.2. There's a couple of things that I want to look at in this particular video, and the first thing is the inclusion-exclusion principle, and it's relating the union and the intersection of the probability of two events happening. So I want to look at that. I also want to look at how odds and probability relate to one another. First of all, I'm going to look at the inclusion-exclusion principle, and we're going to look at an example of this, and then we will look at odds. So, what is the inclusion-exclusion principle? It says that if we've got two different events, E and F, okay, so each one is made up of certain outcomes for an experiment. Then the probability of the union of E and F happening, so remember the union of two events is going to be all the outcomes that land in E or F or both. So it's any outcome that you see occur in either one of those two events. The probability of that new event, E union F happening, is equal to the probability of the event E happening plus the probability of the event F happening, but then we subtract the probability of the event E intersect F happening. Why do we do that? Well, this looks very similar to when we were counting sets, if you go back to a previous section. It's a very, very similar principle. When we look at the probability of E union F happening, we've also added in the probability of the events that land in both E and F. They have been counted twice because they have been counted in the probability of E happening, and they've also been counted in the probability of F happening. So those outcomes that land in both of those events have been counted twice. So the probability of E union F happening is going to be the probability of E plus the probability of F, but then we have to subtract the probability of the intersection happening, as it has been counted twice when we've added the probability of E and the probability of F. So it's very similar to when we were looking at the number of elements in a set. If E and F are mutually exclusive, that means that there are no outcomes that land in the intersection of E and F. E intersect F is the empty set. The probability of the empty set happening is 0. It's never going to happen. It's an impossible event. So because the probability of E intersect F in this case would equal 0, then I can actually reduce this inclusion-exclusion principle down to say that the probability of E union F is just the probability of E plus the probability of F. But that only counts when E and F are mutually exclusive and have no outcomes in common. I'm going to do a quick example of this that we can work through. And this uses that inclusion-exclusion principle. So it says that a factory needs 2 raw materials in order to operate. The probability of not having an adequate supply of material A is 0.05. So 5% of the time they don't have an adequate supply of material A. And the probability of not having an adequate supply of material B is 0.03. So 3% of the time they don't have enough of material B. A study determines that the probability of a shortage of both of those materials is 0.01. So 1% of the time we don't have enough of either of those materials. What proportion of the time can the factory operate? So in order to operate, it needs a good supply of both of those materials. So I'm going to look at the probability of having a shortage of A or a shortage of B. Okay? If we've got a shortage of A, we know we can't operate. If we've got a shortage of B, we can't operate. And if we've got a shortage of both, we definitely can't operate. So I'm going to look at the probability of one or both of those things having a shortage. So I'm going to look at the probability of A union B. That's going to be the probability of having a shortage of A plus the probability of having a shortage of B minus the probability of having a shortage of both A and B. Remember here, I'm looking at the probability of there being a shortage of this. The question actually asks what proportion of the time can the factory operate, meaning what proportion of the time is there not a shortage. So what I'm doing here is I'm calculating the probability that there is a shortage, and then I can subtract it from 1 at the end, and that will tell me the probability that there is not a shortage. Okay, so the probability of A union B is going to be the probability that we have a shortage of A, which was 0.05, plus the probability that we have a shortage of B, 0.03, minus the probability that we have a shortage of both. So that tells me that 7% of the time I have a shortage of one, the other, or both, which means that 7% of the time the factory cannot operate because you have a shortage of at least one of the materials 7% of the time. So that tells me that 93% of the time the factory can operate. Because the other 7% of the time there is a shortage of at least one of the materials. Okay, so always look at the question, and remember the reason I did this particular example is it's a good example of having to read the question. It's asking what proportion of the time can the factory operate. We went ahead and used that inclusion-exclusion principle to figure out the proportion of the time that it can't operate, and then we can subtract it from 1 and then put it as a percentage by multiplying it by 100. The next thing I want to look at are odds. Odds are very similar to probability. The only difference between odds and probability is in probability, we are looking at the likelihood of an event occurring in terms of the total number of possible outcomes. So if you go back to rolling the dice, we said that 1 out of 6 times you can roll a 2. 1 out of 6 times you roll a 3. Okay, so we're looking at it in terms of there are 6 possible total outcomes, and one of those times you will roll a specific number. So it was always relating the probability to the total number of outcomes. With odds, you actually relate the likelihood of an event happening to the likelihood of it not happening. Okay, so whenever they say in odds the odd of an event occurring is 2 to 1, that would tell you that 2 out of 3 times it's going to occur and 1 out of 3 times it's not going to occur. So you've added the 2 together, that would tell you the total number of outcomes that we're looking at, and 2 out of 3 times it would occur, 1 out of 3 times it wouldn't occur. So that would be 2 to 1. Okay, so that's kind of how odds work. It just relates it to the likelihood of the event not occurring, not the total number of outcomes. You kind of have to add them together and do some work with it in order to put it in terms of the number of total possible outcomes. So that leads me to converting between odds and probability, and then we'll look at a couple examples. So let's say if you're given an event E, the odds in favour of an event E are said to be A to B. So let's say the odds in favour of an event E happening are 2 to 1. Okay. Then the probability of the event E can be found by doing A divided by A plus B. Like I said before, if the odds in favour of an event were 2 to 1, then I told you that 2 out of 3 times we've added the odds together, 2 and 1. 2 out of 3 times the event will happen. 1 out of 3 times, or B out of A plus B times, if you're doing it in terms of the algebra here, B out of A plus B times, the event won't occur. A out of A plus B times, the event will occur. So the probability of the event E actually occurring, of it actually happening, are A out of A plus B times. Okay. Going the other way, if you're given that the probability of E is equal to, we'll call it little p, then what I want you to do to convert it to odds is to take the fraction p over 1 minus p, and then I want you to reduce it down and simplify it. And when you've simplified that fraction as far as it will go, then you will have this fraction A over B, and that tells you that the odds are A to B. That's the odds in favour of the event E happening. Okay. So let's look at this again. If you are given the odds A to B, to then give you the probability of the event E happening, you take whatever the odd was in favour, the A, divided by the total number of outcomes, A plus B. So A out of A plus B times the event will occur. If instead you're given the probability, we'll call it little p, and they ask you to find the odds, you're going to do p over 1 minus p as a fraction. You're going to simplify that fraction down as far as it will go, and then that will give you a number on the numerator, number on the denominator. That is what you use as A and B to say the odds are A to B in favour of E happening. Okay. Let's do a couple examples here. So in this example, I'm going to look at the chance of rain. Let's say that they've told you that the chance of rain today is 2 to 5. Okay. What's the probability of it raining today? Okay. So the probability of rain would be, it said that the chance of rain, so the odds that in favour of it raining today are 2 to 5. So that tells me that 2 out of 2 plus 5, which is 7, 2 out of 7 times it will rain. Okay, if it's 2 to 5, you do 2 over 2 plus 5. So 2 out of 7 times it's going to rain. So the probability of rain is 2 over 7. You can put this as a decimal as well, just put it into your calculator as 2 over 7, or you can leave it as a fraction, that's totally fine. We'll do another example which will bring us back to a previous problem that we have done earlier in this chapter, in chapter 6, and that is rolling a pair of die. Okay. If we roll a pair of dice, then we found out in a previous problem that we did that we have a 1 in 6 chance, or 6 over 36 chance, that you would get the same number on both of the dice. Okay, so we found you can write it as either. Okay, Okay, so we found that there was a 1 in 6 chance of rolling the same number on both dice. Okay. I want to now find the odds of that happening. Okay. So what we have to do here is we have to do P over 1 minus P. Okay, I'm going to keep it with the simplified version here, which was 1 over 6. So P divided by 1 minus P. That would be 1 over 6 divided by 5 over 6. If you flip the bottom fraction and multiply, you get 1 over 5. So that tells me that the odds in favour of rolling the same number on both dice are 1 to 5. Okay. Odds in favour of rolling the same number on both dice are 1 to 5. So that tells me that if I were to add those numbers together, 1 in 6 times, I'm going to roll the same number on both dice. 5 in 6 times, I'm not going to roll the same number on both dice. I'm going to get different numbers on each of the dice, okay? So that's what these odds tell us, okay? So whenever you do this problem, when you're given the probability, do P over 1 minus P. Simplify that fraction down, and then here we took that fraction, the numerator was your A value, the denominator was your B value, okay? So that then tells us, once we got 1 to 5, that there is a 1 in 6 chance, we've added 1 and 5 together, a 1 in 6 chance that the event will occur, and a 5 in 6 chance that it will not occur. So that's how we read these odds.